Uh, Before taking up the study of junction field effect transistors, I like to continue the discussion on the common emitter configuration. We have seen that the output characteristics of a common emitter amplifier is like this, with the voltage collector to emitter voltage given here and a collector current given here. So collector current is given in milliamperes. Please note that the characteristics is almost similar to the common base configuration characteristics, but there it is the collector to base junction potential, whereas the output potential of interest here is collector to emitter potential VCE. The difference between these two is one junction potential, PN junction potential. Therefore, this characteristic can be obtained by shifting the previous characteristics. There is one more difference. You will find that the slope is very small in the other characteristics, whereas here the slope is slightly larger than in the other case. We shall see what is responsible for that. If you look at the current expression, it will be clear that this is what happens here. Now we know that in a transistor, the collector current, an expression for the collector current is like this, is equal to minus IC is equal to minus alpha IE minus IC BO. So this is the expression for the collector current, and we also know that IC is equal to minus IE plus IB. The reason is it's a three-terminal device. We have IE, IB, and IC going into the transistor. By applying Kirchhoff's current law, sum of these currents is equal to 0. Now substitute this expression in the upper expression, and you will find that by substituting this, you will find that IC is equal to alpha IB by 1 minus alpha minus IC BO by 1 minus alpha. So please refer to this expression, this diagram. So you have IE going in, and actually IB is coming out, IB goes out, and IC goes out. Therefore, this IE is equal to the outgoing IB plus the outgoing IC. By convention, we took incoming IC as positive and incoming IB as positive, and so on. Therefore, IC is negative, IB is negative, and IE is positive. And IC is equal to, since the sum of these three currents is equal to 0, we have IC is equal to minus of IE plus IB. And we also know that the IE, which goes into the transistor, alpha times that goes out of the collector, and only 1 minus alpha times this goes out as the base current. Okay, so hence this is the expression for that, and substituting this in this expression, you will find an expression for the collector current in this form. Now, when the emitter current or when the base current is 0, that means the base is open circuited. So what is the current that flows in to the into the emitter, and naturally that's what comes out of the collector. IC is equal to minus IE in this particular case, then IB is equal to 0. If you substitute IB equal to 0, so you will find that this IC is minus ICBO by 1 minus alpha. ICBO is the PN junction reverse current, which is equal to IC naught of a diode, and which is of the order of a nanoampere in the case of silicon transistor, and it is of the order of a microampere in the case of a germanium transistor, and alpha is of the order of 99%. If that is so, please note that IC is equal to 100 times ICBO. So whatever is the cutoff current you obtain in the common base configuration, 100 times that will be obtained in this. This current is actually ICEO. The current going into the emitter and coming out of the collector when the base is open circuited, and this is, as I said, 1 by 1 minus alpha. That means a large factor, okay, multiplied by the cutoff current in the case of a common base configuration. So this current is larger than that, and partially this factor, and this is, please note that this is the cutoff current, and once again I invite your attention to this expression. So if I can rewrite this expression as, so beta times IB minus, so this would be 1 plus beta times ICBO, where beta is equal to alpha by 1 minus alpha. Beta is equal to alpha by 1 minus alpha, in which case 1 by 1 minus alpha is going to be 1 plus beta. I am defining a new term beta. This is known as DC current gain of a common emitter amplifier. It is because of this reason that in a common base amplifier, the input current that flows is equal to IB, and the output current that goes out is, or that goes in, is IC. Therefore, the gain, output current by input current, is a current gain. So that current gain is, in this particular case, IC by IB is equal to beta, when this is negligible, ICBO is negligible. Therefore, this beta is known as DC current gain. And what is its magnitude? When alpha is 0.99, it is of the order of 100 or 99. It is 99. Therefore, the current gain, DC current gain, is very large in the case of a in the case of the common emitter configuration. And with increased collector to emitter potential, so you will find that there is a rise in the, slight rise in the collector current, because partly it is because of a larger amount of diffusion that takes place. So diffusion content slightly increases with an increased potential over here. As a result, the slope is slightly larger than in the common base configuration. And because beta is of the order of 100, for 10 microamperes, you are getting about 1 milliampere, and 20 microamperes, 2 milliamperes, and so on. Please note that these are all negative figures because of the convention we are following. So this is what is known as common emitter configuration. Please note that the collector current is proportional to the base current in this region. So, in this region the collector current is proportional to the base current. Outside this region here the collector current is smaller than beta times IB. Therefore, this region is known as the saturation region. And here when IB is equal to 0 or below IB equal to 0, IC is almost 0. It is a small quantity. IC is a small quantity, it is equal to ICO. Therefore, this region is known as the cutoff region. This region is known as the cutoff region. In the saturation region, you will find that it is of the order of the saturation voltage is of the order of 0.3 volts. So, in the saturation region, the base to emitter junction or the emitter to base junction is definitely forward biased with about 0.6, 0.7 volts being the drop here, and the base to collector junction is also forward biased. For proper operation, we want this junction to be forward biased and this junction to be reverse biased. And please note that when you reduce the collector to emitter junction potential, collector to emitter potential below about 0.7 volts, so this junction becomes positive biased. And when this is positive bias, this is also positive bias, it is saturation region. Then what happens when this is positive biased? As I told you, the potential difference which accelerates the injected holes is no longer present. As a result, the current, that is the charge carriers that are injected inside, goes out of the base, and IC is equal to beta IB is no longer valid. Hence, IC is less than beta IB in this region, okay, and it is known as saturation region. And this region in between is known as the active region, because if you want to make use of the transistor as an amplifier, you have to operate the transistor at some collector current and some collector to emitter voltage in this region. It is obvious that collector to emitter voltage is larger than about 0.3 or 0.5 volts, and it is obvious that base current is the magnitude of the base current is definitely more than 0. Okay, so that is the active region. Active from the point of view of amplification. Well, by the side of this, we can also use a transistor for switching purposes. You can see that the transistor is on, that means in the saturation region, or it is in the off in the cutoff region. And by operating the transistor in this kind of modes, either in the saturation region or cutoff region, you can have binary level switching. That's what you have, that's what we do in the case of computer circuits. We make use of a transistor and make the transistor work in the switching mode, transistor as a switch, where we like to operate the transistor either in the cutoff region or saturation region predominantly. Of course, active region also is also used. So, in the cutoff region, we expect the collector current to be almost 0. But in this particular configuration, common emitter configuration, so this ICEO is about 1 plus beta times ICBO. ICBO, like in the common base configuration, it is of the order of a nanoampere. and here it may be 100 nanoamperes, which is not as small as in the common base configuration. Therefore, if you intend to make this current 0 in the cutoff region, what we normally do is we slightly reduce the potential over here. The emitter to base junction potential is further reduced to see that this IC is less than this. We will discuss more about it when we discuss about the transistor as a switch. Any questions on the common emitter configuration? At this stage, I like to change the notation. Okay, let me consider a PNP transistor. When you use it in common emitter configuration, you have IE, actual IE going in, IB actually coming out, and IC going out. So because we were using the convention as the ingoing currents as positive, we have IB plus IC plus IE equal to 0 in the previous case. Now in this particular case, IE is equal to IB plus IC. Whatever is going in comes out of these two, and nothing is created inside. Therefore, IE is equal to IB plus IC in the case of a PNP transistor. In the case of an NPN transistor, actual IE goes out here. This is IE, and this is equal to this IB, which actually goes in, and this IC which actually goes in. And this IC is beta times IB, and IE is naturally IC plus IB, another IB. Therefore, IE is equal to 1 plus beta times IB. The same thing is valid in this particular case also. If you treat this as your IE, the same expressions are valid. The difference is only in notation. In different books, you will find that different notations are followed. That's why both were discussed here. So there is another configuration of the transistor. It is common collector configuration. In the common collector configuration, say this is an NPN transistor. We apply the signal at the base junction, base emitter junction in this form, and take the signal over here from the emitter. This is our load resistance. So you apply the signal over here to the base, and you will take the signal across the RL. That means the incoming current, the input current is the base current, and the output current is the emitter current. And please note that between these two, you have a ratio. In the case of DC currents, you have the ratio of 1 plus beta. So therefore, the DC current gain over here is going to be 1 plus beta. And for alternating signals, but we define the gain for alternating signals. So that gain is also of the order of 1 plus beta. It's different, but it is of the same order. Since both these voltage sources are appearing between the base and the emitter, you won't find any voltage amplification. This will be clear when we discuss about this will be further clear when we discuss about the small signal analysis of a transistor. Any questions? I would like to recall the common base configuration. I didn't discuss about what is the saturation region, what is the cutoff region, and let me just point out which region is cutoff region, which region is saturation region over here. Extending the same argument of the common emitter amplifier, so please note that this is the cutoff region in the case of common base characteristics, because the emitter current is 0 here, collector current is also almost 0. And so below 0 volts is the saturation region. Here, that means when VCB is negative, it is a saturation region. For VCB greater than 0 and for IE greater than 0, it is the active region. I repeat, we can use the transistor as an amplifier in this region. Now let us discuss about, okay, before going into that, please note that in this kind of transistor which we have used here, we have the holes and the electrons both as the charge carriers. Both are involved in carrying the current. Therefore, it is known as a bipolar device. We have charge carriers with positive polarity and negative polarity, both involving in the process of current, in the process of conduction. Therefore, such devices are known as bipolar devices, and the transistors are known as bipolar junction transistors, BJTs. There are different manufacturers who make the transistors, and there are different type numbers for these transistors. So the National Semiconductors use this symbol 2N2222 is a transistor, CIL 490 is a transistor. These are all type numbers. 2222 is a type number for that particular transistors, 490 is a particular transistor, and depending on the voltage ranges in which they operate, there are different versions. There are power transistors who work up to hundreds of volts and 1 or 2 amperes or even more. And most of the transistors, small signal transistors, work in the milliamperes and so tens of volts range. So let me briefly discuss about it. So look at this plot. So this is the output characteristics. The collector current, maximum collector current that can be allowed to flow through the transistor without damaging the transistor is fixed. So that is known as IC max. So this is one rating of a transistor. We should not operate the transistor at a current more than this. If you operate it, the transistor will get burnt. Similarly, you have VCE maximum, the collector to emitter voltage, the maximum collector to emitter voltage may be say 30 volts. So for a particular transistor. So that means the VCE max should never be operated, VCE should never be operated above 30 volts. There is another specification, power dissipation, PD max. In a junction transistor, the power dissipation is approximately equal to the collector current into collector to emitter voltage. IC into VCE is the power dissipation, approximately equal to the power dissipation. It's a 3-terminal device. If you consider here IE into the IE is the current which flows in, IB which goes out, and IC which goes out, and the maximum amount of voltage drops across this in the active region. Therefore, VCE into IC is considered to be almost the power dissipation in a transistor. And the transistors have certain power dissipation capability, and you should not go beyond that limit. A typical power dissipation capability is 300 milliwatts. Okay. So if you, in the strict sense, if you find out IC into VC equal to constant, curve would look like this. PV is equal to constant kind of curve. So if this is, say, PD is equal to PD max curve, that means if you operate the transistor at high collector current, you see that VC is low. Or if you are operating it at a low collector current, you can go for a larger VC, so that the power dissipation, that is IC into VCC, is within that limits. So for making use of a transistor as an amplifier, you have to work in this region. Now you have, other than the bipolar junction transistors, you have some other interesting transistors available. So these are field effect transistors. The field effect transistors have certain advantages over the bipolar junction transistors. So such transistors occupy small space and more stable operation. And also low power. So because of this reason, many transistors can be put, millions of transistors can be put onto a small chip, and you have highly complex computers available on a single chip. So that is a great advantage. Imagine millions of transistors putting on a square inch, 1 square inch, put on a 1 square inch. So that is the order of technology nowadays. And power. If each transistor consumes, say, 100 milliwatts of power, a million transistors consume 100 kilowatts of power. Imagine your home computer consuming that much of power, or the calculator consuming that kind of power. You can't think of using it in practice. So it is because of the field effect transistors, which operate in microwatts power range. We have that 1 million transistors putting on a chip, still the chip consuming small amount of power and not heating up the environment. Okay, that is possible. So this field effect transistor has such an advantage. So let us look at how this device works. And before discussing about that, so let me mention that there are 2 kinds of these field effect transistors. One type is the junction field effect transistors, which naturally work with a PN junction, and the other one is metal oxide semiconductor field effect transistor, MOSFET. In fact, out of these two categories, it is the MOSFET which gives you the advantage of small space and very low power, MOSFETs. Okay, but here in your syllabus we are going to discuss about the junction FET, which is more used for amplification rather than switching application, which is common with digital circuits like computer circuits. So here is the construction of a junction field effect transistor, JFET. Typically, we have an N or P type bar of semiconductor. As an example, let us consider an N type semiconductor, N-type semiconductor bar. So into which we embed some P-type doping. So because of which a P-type material is formed here. Imagine this as a cylinder and you have a ring, a P-type ring on it. And here is the cross section drawn across this. And say you make some ohmic contacts here, which are metallic contacts. Now we are talking about ohmic contact. Why? We know that when we form a junction with two different types of materials, so they behave in a different way, like a PN junction. Okay, so that means this junction ohmic contact doesn't act like a rectifying junction like a PN junction, but it's a direct contact for current flow without any additional activity. So this is a P-type, N-type semiconductor material with two terminals brought out. And naturally, as you have seen earlier, so this one acts like a resistance, this N-type material, with the conductivity given by omega mu into N, what we have discussed earlier. Now, therefore, if you apply some potential over here, so you will find that current flows, and this one acts like a resistance, as long as you don't do anything with the P-type junction. Now, if you make a contact, ohmic contact here with the P-type material, and naturally all this P-type material is connected together, and say you call this as the gate. So we call this as the drain and the source. Between the drain and source, it is a resistor, and we have a junction formed here, and we call that as the gate for a different reason. So now you connect this gate to the source and see what happens. Well, when this is connected and the potential is very small, this one acts like a resistance. But when the potential is large, please note that the voltage, say if it is 2 volts, so this 2 volts gets dropped uniformly across this along this material, assuming that the cross section is uniform. So in between, if you find the potential, it may be 1 volt, here it is 2 volts, and here it is 0 volts, and here it may be about 0.5 volts, and it may be 1.5 volts. So this is what is the potential distribution along this resistive semiconductor. Now, because there is a positive potential applied to this semiconducting material, of course that positive potential is varying, here it is 0.5 volts, here it is 1.5 volts, and now if you connect this gate to this 0 potential, what do you observe between this p-type material and n-type material? So this junction is reverse biased. When this junction is reverse biased, PN junction, naturally you have a depletion region forming around this junction. So you have the depletion region formed. So the charges are, this region is depleted of mobile charges because of the reverse bias junction, and only mobile charges are now confined to, and what are the majority mobile carriers over here? Electrons are the majority mobile carriers, and these electrons are available only in this part. These are not available here because of the diffusion that is taking place. And so there would be, you will find positive space charge here, negative space charge here, but no mobile charges. And as a result, the area of the n-type semiconductor bar goes down, and the resistance increases. And when the resistance increases for the same potential, so the current goes down. Or as you increase the current, as you increase the voltage, current increases initially. Then when the space charge extends because of this voltage difference, when the space charge extends deeper into the n-type bar, its resistance increases and current remains almost constant. Hence, the current, the voltage current relationship, so this is VDS, drain to source voltage that is applied. This is the drain current. You observe, if you plot the drain current versus drain to source voltage, you will find that it increases initially up to certain level, and after that you will find that the current remains constant irrespective of an increase in the drain to source voltage. So this voltage may be typically, this voltage is typically about 2 to 3 volts. This is what happens. And naturally this voltage depends on the dimensions and the doping concentration. Okay, so this current remains constant. This is, I am talking about when VGS is 0. Now what happens if we reduce VGS? If we make VGS as negative, if VGS is made negative, what happens to the situation? If VGS is negative, even when this potential difference is 0, this PN junction is reverse biased. Therefore, even to start with at 0, almost at 0 voltage itself, the resistance is larger than when this is 0. The gate to source potential VGS is 0. Okay. So as a result, you will find that the resistance of this bar is large and the characteristics is something like this. This is for VGS is say minus 1 volt, and for VGS is say minus 2 volts. The curve is like this, say minus 3 volts. It is like this. And for certain VGS, this region is completely, the depletion region extends to the full cross section, and this is almost 0, and it almost touches each other, these two regions, in which case the channel is totally pinched off, and as a result, so you will not find current flowing, no appreciable current flows in that situation. So for VGS, some very small VGS, ID is almost 0. For a large negative bias, ID is almost 0. So this is what you find. And please note that this kind of drain to source can be interchanged also. In this device, drain to source also can be interchanged if it is symmetrically built, in which case the same kind of characteristics is applicable on this side also. Well, if you change the drain and source, so this becomes your source, this becomes your drain, and the potential should be with respect to this. Even if this VGS is with respect to this and not with respect to that, we have the same kind of characteristics, so that is applicable. Therefore, so this device acts like a resistance up to certain voltage level known as the pinch off voltage, and beyond that the current remains constant. Very interestingly, because of this reason, this device can be used as a voltage dependent resistance. When VGS is 0 volts, so this is the resistance value is equal to the slope of this curve, inverse slope of this curve. When VGS is minus 1 volt, VGS is minus 1 volts, the resistance value of this device is inverse slope of this, and minus 2 it is the inverse slope of this. Therefore, it can be used as a voltage dependent resistance. So this resistance depends on this voltage. Okay, any questions? So we shall discuss about this device further in the next class.